So now we are going to be discussing just a couple or a few practice problems that essentially demonstrate what I want you to know for the exam and what I kind of want you to lead with. And so obviously, since this is more of a conceptual class, I don't want the math to be so difficult. A lot of this actually just has to do with making the correct assumptions and basically dissecting these problems so that they become a lot easier. So the first one that we have here is a man runs 6 meters in 3 seconds in the south direction. What is his average speed and average velocity? And so what we really, these are actually really easy to do. You probably already know the equation that you can use, but I'm just going to try to do a simple systematic approach to solving these problems. So the first thing I want to do is write down what I'm trying to solve. So the first one I'm trying to solve for is average speed, and we're also solving for average velocity. They're going to end up being like really similar. What we have is we actually have a change in x, which is 6 meters south. And then we have our time, which is 3 seconds. And let me use a little bigger pen. There we go. So we have these, we look at the equations we have, and the two that we have, they're essentially the same. We have average speed is equal to your distance over your time, and we also have your average velocity is equal to your change in, change in distance or displacement over time. And so something you might be thinking of is, well, I don't have x, I only have a change in x, so what does that mean? Well, if we were to draw this problem out, we essentially have a guy starts at this point, and then he runs down 6 meters. What is his distance? It's 6 meters, so we can plug that in. We don't need that direction. So when we do this, we have 6 meters divided by 3 seconds, we get 2 meters per second. That's his average speed. For our velocity, it ends up being really similar, except we have also that direction, but I'm going to include that in later. So we also have our 3 seconds. That gets us 2 meters per second south. So pretty easy, not too hard. Yeah, sometimes drawing pictures will be helpful, but if you understand how to do these equations, these ones are they should feel pretty easy so far. This next one is when we start introducing one of the basic kinematic equations. So now the same man, after running for 3 seconds above, decides to increase his speed by accelerating at a rate of 2 meters per second squared. And this is assumed then that this is going to be in the same direction that his displacement was in. So thinking about it this way, if this was a 6 meters in the south direction and we were positive, then essentially we could say that that is positive, and so our downwards is positive. So maybe that can be tricky sometimes, but if you're ever confused about which direction is which or something like that, definitely contact me and let me know, specifically for when I write these problems, because I want to make sure they're as clear as possible. So the same man runs for 3 seconds above, decides to increase his speed by accelerating at a rate of 2 meters per second squared for 3 more seconds. What's his final speed and final velocity immediately after this acceleration period? So we write down what we're trying to find out. So in this case, your speed, since we're just still running in a straight line, is just going to be the magnitude of your velocity. So that's actually going to end up being much easier. So I'm not going to actually try and solve for his final speed. I'm just going to solve for the velocity and then chop off the direction. So we're looking for a v final this time. Right. Things that we have a time, which is 3 seconds. We get it from this one right here. This one is from above, so that's misleading a little bit, but I mean, same time, so I guess it doesn't matter too much. We have an acceleration that is equal to 2 meters per second squared. And that's kind of all that we're given. If we look at the different final velocity equations, there are 2. So we have v final squared equals v initial squared plus 2a change in x. If you're wondering where these are coming from, if you go back and watch the kinematics video, they kind of explain kind of where they come from. I'm not too concerned with you knowing how to derive them, just that you know them, and that you know what they look like. the other one that we have is v final equals v initial plus acceleration times time. So technically speaking, if we were to draw the situation out, all we know is that first this person runs down for 6 meters over 3 seconds. And then at this point right here, we'll call this point A, call this point B, he starts accelerating. Right, so now he's going to be going faster, so we can assume this vector is maybe a little bit bigger. And at point C, this is where we're trying to find our velocity at. So the velocity at point C is our final velocity. We don't know what this change in x is. We don't know that, right? So if we don't know that, that's not going to be helpful to us. Something that we do know is the velocity at point B, right? We know that he is running at a constant speed from A to B. So if he's running at a constant speed from A to B, whatever his average velocity was from the previous problem, that will be his initial velocity. So from the previous problem, we had 2 meters per second south. So our initial velocity is then 2 meters per second south. Just put a little s. So what we have here is we have 3 variables, and knowing that we can't find our displacement right away, we have one equation that will work for us. And so we'll simply write that out and plug it in. So you have v final plus v initial plus acceleration times time. And we just plug everything in. So you have our 2 meters per second south plus our acceleration, which is 2 meters per second squared in our same direction, multiplied by our time, which was 3 seconds. Right? Notice really quickly that our units cancel out. So we just have it's 2 meters per second times 3 plus 2 meters per second. So that's good. And acceleration multiplied by time is a velocity. So that's good because if it was a different unit, we wouldn't be able to add them together because math would not allow us to. So we get 2 plus 6. If we add that together, we get a v final of 8 meters per second, specifically 8 meters per second south is our v final. So that's our final velocity. And then our speed final, right, our instantaneous speed would just be 8 meters per second. Something else that we could say is if I asked you what's the magnitude of the speed, you would just be 8 meters per second. And again, with this problem, downwards was denoted as our positive direction. So keep that in mind. So our last problem is going to be a bit of a doozy. It has a bunch of parts. And this is where I guess the math can get a little bit more confusing. So a ball is thrown straight into the air and has a hang time of 4 seconds. What height did it reach? Or what was the initial and final velocity of the ball? So there are some assumptions that we can make with this problem. So let's first draw it out. It's thrown straight into the air, but it's hard to draw a ball thrown straight in the air. So I'm just going to draw this, and it kind of comes up, comes back down. Even though there's a little arc here, I'm assuming that this is straight up and straight down. So some assumptions we can make. The first one is I'm going to make some points here. Pull in here, pull in here. We're going to call this point A. This is going to be point C, and up here is going to be point B. So the first thing, the velocity at A, if this is a flat ground, is equal to the velocity of C. And for all these problems, I'm probably not going to give you any non-flat ground problems, so don't worry too much about that. Another thing that we can find is that the velocity at point B is equal to 0. This is because right at point A, as it goes up, it slows down, eventually hits 0 meters per second, and then it starts decreasing in speed, or i.e. changing its direction, going more downwards. So first, what height did it reach? So we are looking for a change in x. Specifically, it's either from A to B or the change in x from B to C. I'm going to tell you right now, finding the change in x from B to C is going to be much easier just because everything's going to kind of be moving in the same direction. If you find the change in displacement or the height using A to B, then you have a negative gravity. You'll have an upward moving ball. It can be a little bit messy. Another assumption that I forgot to mention is that the hang time is the total time that the ball is in the air. So for the ball going from B to C, time from A to B or B to C is equal to 2 seconds, where the time from A to C is equal to 4 seconds. So we can just cut that right in half. So that's pretty helpful. So if we choose our 2 points as just B to C, then we're just going to be using this stuff right here. So we're looking for this. Our hang time is 2 seconds. Our acceleration is just gravity, and that's 10 meters per second squared. Again, at this point, we can denote that, set our frame of reference, downwards is positive. And we're looking, and then the last thing that we know is our initial velocity. So the velocity at B, or our initial velocity, is equal to 0. So what we need to do is essentially find an equation that has these 4 variables in it. The one that I can immediately think of is change in x is equal to VIT plus 1/2 AT squared. And so all we need to do is plug this stuff in. Our initial velocity cancels out because we have that 0 right there. And then we just plug in this 1/2 AT squared. So we have 1/2, gravity is 10, multiplied by time squared, which is just 4. And so this actually says 4 seconds squared. So if we look at our units, right, those cancel out. So we really just we're left with meters. So that's good, because if we're left with meters, we're trying to get or end up with a height. That sounds just about right. So we have a change in x equals 1/2 times 40, which is 20 meters. So that's the distance. This actually, what we technically solved for was the displacement from B to C, which is a downwards direction. When we're looking for height, we're kind of just looking for how much. So we wouldn't say 20 meters down. We would actually just say 20 meters, and that would be enough. So that's pretty easy. When we look at what was the initial and final velocity of the ball, the nice thing is that if we find the initial or the final, they're going to be the exact same. And something that I need to go back to, and I keep doing this, and this is my fault. VA is not equal to VC. The velocity at A is actually equal to the velocity of C. So they have the same magnitude, but they're pointed obviously in different directions, right? My mistake. I always do that on accident. So if we were to solve for this one, well, if we already have almost all the information for the BC portion, let's use that. So I know my change in x now, but that's probably not going to be too useful. The easiest equation that I can know or use is this one right here. And we pretty much already have all that stuff. Looking up to all this information right here, if we're looking for using the B to C information, well, initial velocity is 0, acceleration is 10, and our time is 2 seconds. Well, that's 20 meters per second. So our V final is 20 meters per second. That means our V initial is also 20 meters per second. However, again, depending on which ways are positive, which ways are negative, one has to be positive, one has to be negative. This whole time we've been denoting downwards as positive. So our V final will be our positive one, and our V initial will be our negative. So there you go, right there. And so you might be looking at this and it might look a little bit daunting, but it's all just about setting up yourself for success, writing down what you need to find, what assumptions you can make, and if those assumptions allow you to find even more things out. This number 3, I feel like is a pretty standard problem, so definitely go back through this, try to follow along with what I did, plug in different numbers, and always check to make sure that your information or your answer makes sense. So that is all I have for you. If you need more help, please send me an email, and I'll try to get back to you as soon as possible. So even during the test, if you need a little bit of clarification or something like that, that's totally fine. So have a good one.